Hi again, it's always Ludovico Biagi from Politecnico di Milano. This slot of slides is relevant to the definition of random variables, both continuous and discrete, and their properties. So let's start with the definition of a random variable. A random variable, RV, represents the process of assigning a real number to every outcome of an experiment capital omega. So we have an experiment capital omega, we have possible outcomes of the experiment that in this picture are named omega 1, omega 2, omega 3. To each one of these outcomes we can assign a corresponding real number in the real axis. So for omega 1 we have x1, for omega 2 we have x2, and for omega 3 we have x3. A random variable is such that given each one x that belongs to R, the real axis, defined AR the set of omega such that x of omega is smaller than x, this set AR belongs to capital omega. So, in other words, a random variable is a function that has domain in the set of the experimental outcomes and range in a set of number belonging to the real axis. Another way to say is that x maps capital omega to R. All the random variable in the following will be written in capital letters. Now, for a given random variable, we are able to answer to the following question. What is the probability that the random variable x is smaller than a given number? So the probability of x smaller or equal to x signed. This is clearly equal to the probability of all the outcomes omega such that the output of omega is smaller than x signed. What is the probability that the random variable x is comprised between the numbers x1 and x2? Written in mathematical way, it is probability that x1 smaller than x smaller than x2. In this case, we are looking the probability of all the outcomes, omega, such that the output of omega is comprised between x1 and x2. So if we know the probabilities of the different omegas, we can compute the probability of the random variable. Let's suppose you have two launches of two dice, or two consecutive launches of one dice, and write the possible outcomes in terms of the sum of the extracted faces. So x equal to 2 is generated only by the event 1, 1. X equal to 3 can be generated by the event 1, 2, but also by the event 2, 1. The event x equal 4 can be generated by the event 1, 3, or the event 2, 2, or the event 3, 1. And you can continue up to the event x equals 12 that clearly can be generated only by the event 6, 6. So, given that the probability of each one extraction of omega is 1 over 6 multiplied by 1 over 6, so 1 over 36, we have the corresponding probabilities of the random variable. X equal 2 as probability 1 over 36, exactly as x equal 12, because they are generated only by one possible event. X equal 3 has a possibility of 2 over 36, x equals 4 is a possibility of 3 over 36, and so on, exactly as you find in this table. Let's go to define a new quantity that is the distribution function. Given a number x, we can form the event omega such that x of omega is smaller than x, smaller or equal. This event depends on x clearly. Therefore, its probability is a function of x. This function is called cumulative distribution function. So fx of x is the probability that capital X is smaller or equal to the given x, and it is the probability that of the events omega such that x of omega is smaller or equal to given x. This for each one x belonging to R. What are the properties of the distribution function? The function f is monotonically increasing. In particular, so means that if x1 is smaller than x2, the fx of x1 is smaller than fx of x2. Fx tends to 1 for x that tends to plus infinite, and fx tends to 0 for x that tends to minus infinite. The probability that x is bigger than given x is 1 minus the cumulative distribution of fx. The probability that capital X is comprised between x1 and x2 is given by fx of x2 minus fx of x1. This holds for each one x1, x2 belonging to R, x1 smaller than x2. And finally, the function, the probability cumulative distribution, can be either continuous or discontinuous. In particular, if the experiment omega consists of a finite number of outcomes, fx is a staircase function. And this is also true if omega consists of infinitely many outcomes, but x can take only a finite number of values. That means that for every subset of omega, just one x value is assigned. And so, for example, for the sum of two dice roll, the cumulative distribution function is something like that. You see in this example, exactly in the previous table, that the probability of the outcome 1 is 0, because the sum of two faces cannot be 1. The probability of 2 is 1 over 36. The cumulative probability of 3 is the probability of 3 plus the probability of 2, so it is 4 over 36. The probability of 4 is the sum of probability of 4 plus 3 plus 2, etc., 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 up to the probability of 12, that is equal to 1. Now, let's look a little bit deeper in this continuous distribution function. Let's examine its behavior at a discontinuous point. For example, in x0 equal 3. We can define three kinds of limit. The limit of f that tends to 3 minus. What does it mean, tend to 3 minus? In practice, the probability that x is strictly smaller than 3. That means, in this specific example, the probability that x is equal to 2, and it is 1 over 36. Now, we can define the probability that fx tends to 3, but in the meaning of x smaller or equal to 3. In this case, the probability is 3 over 36. Now, the last limit we can consider the probability that, the limit of f of x for x that tend to 3, but from the right, so 3 plus. In this case, again, the probability is the probability of x smaller or equal than 3, and it is again 3 over 36. So we have an important property. The limit of f of x that tends from the right minus the limit of f of x that tends to the left is the probability of x smaller or equal than 3 minus the probability of x smaller than 3. So it is exactly the probability of x equal 3, and it is again 2 over 36, practically as expected. Now, this was a cumulative distribution function, discrete. What about continuous random variables? We can say that a random variable x is continuous when its distribution is continuous for every x. So in this case, the limit for x that tends to the left to a certain value must be equal to the limit of x that tends to the right to the same value, and it is exactly f of the assigned value. In particular, in this case, the punctual probability that x assumes a given value is equal to 0, clearly. The probability that x is smaller than a given value is the probability that it is smaller or equal to that value and is exactly f of the given value. The probability that x is within the interval x1 and x2 is given by f of x2 minus f of x1. So, we will say that a random variable x is a discrete random variable if its distribution is a staircase, not continuous function. In case of continuous random variables, we can use the distribution function to determine the probability that a random variable x takes values in a given interval in an arbitrary region of the real axis. These results can be expressed in terms of derivatives. So we introduce lowercase f of x, that is the derivative of capital F of x, assuming that it exists everywhere. So, the derivative of the distribution function is called probability density function, or simply density function. It is defined as with the symbol small f of x, and it is defined as the limit for, in every point, is defined as the limit for delta x that tends to 0 of capital Fx evaluated in x plus delta x minus capital F of x over delta x, or, if you prefer, the limit for delta x that tends to 0 of the probability that the random variable is comprised between x and x plus delta x divided by delta x. What are the properties of the density function? First of all, the cumulative function is monotonically increasing, so its derivative, the density function, must be positive everywhere at the limit equal to 0. Second property, if we take the density function, if we make the integral from x1 to x2, we can obtain that it is equal to the cumulative function evaluated in x2 minus the cumulative function evaluated in x1. But this is exactly the probability that our random variable takes values comprised between x1 and x2. So, the area of the integral of the density function in an interval x1, x2 equals to the probability that x belongs to this interval. How the cumulative function and the density functions are related? The cumulative function in a point x of the real axis is simply the integral between minus infinite and x of the density function. And clearly, the integral between minus infinite and plus infinite of the density function is equal to 1. That is the so-called normalization condition. Now, let's investigate more in detail the probability function of a discrete random variable. Let's suppose that the cumulative function is a staircase function with discontinuities in certain points xe. In this case, the random variable takes the value xe with a probability of random variable equal to xe equal to bi. It is equal to fx in xi minus fx in xi minus, as we have defined before. The number pe will be represented graphically by vertical segments in the point xe with 8 proportional to pe. In some place, we will use for discrete random variable the notation pe equal to density function evaluated in xe. The function fx, defined in such a way, will be called point density, pointwise density. Note that its values are not the derivative of the cumulative function, but they are equal simply to the discontinuity jump of the cumulative function in that point. Now we go to see some example of random variables, firstly in the discrete case and then in the continuous case. Why we are introducing them? Because they have specific distribution and they represent specific possibilities of outputs of typically experiments. So we don't need to specify the underlying experiment. We are just giving the properties of the distribution cumulative, and we can derive the density function, and we simply assume that the underlying experiment is the real line and the outcomes are the values x. The first one is the so-called Bernoulli random variable. It is discrete. A Bernoulli random variable can assume just two values, 0 and 1. In particular, the probability of 1 is defined by p. The probability of 0 is defined as 1 minus p. So if we want to picture the density, point density function against the real axis, we have just two values for which the density is different from 0, that are exactly in 0 and 1, and in particular the value of f in 0 is 1 minus p, the value of f in 1 is p. Let's go to the cumulative distribution. We need to distinguish three possible intervals correspondingly to the definition of the random variable. We see that for x smaller than 0, the cumulative distribution is equal to 0. What happens passing per 0? We are cumulating the probability of 0. So in 0, the cumulative distribution has a discontinuity of exactly 1 minus p. Then it doesn't change until 1, so it remains constant, equal to 1 minus p. And then we have a new discontinuity because we have to add the probability of x equal to 1. The probability of x equal to 1 is exactly p, so the cumulative function after 1 is 1 minus p plus p, that means 1. A discrete random variable is said to be binomial when the probability to extract the values comprised between 0 and n, let's call k the value of the extraction, is equal to n binomial k multiplied by p raised to k multiplied by q raised to n minus k, where k clearly can range from 0 to n, and p più q must be equal to 1. The binomial distribution is originated by all the experiments of independently repeated trials, when we define x as the number of successes of an event in n trials. For example, the number of extraction of heads in a certain number of launches of a coin. In this case, A is the event head, whose probability p is 0.5, x is the number of heads in the n repetition. Now we can move toward the continuous random variables. Even in this case, we will focus on the main, the most important ones, most important because in statistics they are very useful to describe practical outcomes of practical experiments. The uniform random variable. X is uniform or uniformly distributed in a given interval AB when the density function of x is equal to 1 over b minus a in the interval AB and 0 otherwise. So from a graphical point of view, what you find is that you have the real axis, the value of the density function, a certain value a in the real axis, a certain value b in the real axis. In the interval ab, the density function is flat with value 1 over b minus a. You see clearly that the integral of this specific density function between a and b, or in general, pardon, from minus infinite to plus infinite, is exactly equal to 1 as it is required. What is the corresponding cumulative distribution? It is clearly a linear ramp. Remember that the density distribution is the derivative of the cumulative distribution. So capital F of x is equal to 0 for capital X smaller than a. It is equal to 1 after b, and in the interval in between a and b, it increases linearly as x minus a over b minus a. You see that the specific function, as expected, for x equal a is 0, for x equal b it is 1, exactly as indeed we expected. Another kind of continuous random variable is the exponential one. The exponential random variable has a density distribution given by this formula. The density distribution is 0 for x smaller than 0, and it is equal to some constant positive multiplied by the exponential of minus cx for x bigger than 0. So in this slide you see the shape of f of x. You see that in practice it is equal to c in 0 and tends to 0 for x that tends to infinite. Let's look to the face of the cumulative distribution. The cumulative distribution can be obtained by integrating the density distribution, and it is 0 for x smaller than 0, and it is equal to 1 minus a to minus cx for x bigger than 0. So you see that the function tends as 0 in the origin, and tends to 1 for x that tends to infinite. If you are not familiar with integration, it is more easy to understand by deriving the cumulative function and by looking that the derivative of the cumulative function is exactly equal to what we have said to be the density function. This is a practical suggestion in order to make in general computation. Now, a very important random variable, very important because it is used to describe measurement errors in the statistics applied to observations, and so actually it is very important. A random variable is distributed accordingly to a Gaussian distribution or to a standardized normal distribution when its density function is given by the formula you can read there. You see that there is a multiplying coefficient, 1 over square root of 2p, that is not function of x, that multiplies the negative exponential of x squared over 2 squared. The picture of the function as this shape shown below, it is like a Mexican hat, and it is symmetrical around 0 clearly. And what other to say, the integral, it is not so easy to prove, to compute, but the integral is equal to 1 over the whole real axis. Let's look to the corresponding cumulative distribution. The integration is simply the integration from a symbolic point of view, the cumulative is simply given by the integral between minus infinite and x of the density function. So 1 over the square root of 2p that multiplies the exponential of minus xi squared over 2 index c. If you make the plot of this function, it is not immediate, but if you make a plot, you see that the shape of the cumulative function is something like a sigmoid. In the 0, the value is exactly 0.5. In minus infinite, as usual, it is 0. In plus infinite, it is plus 1. And the function is even because the derivative is symmetric, and so the cumulative function in minus x is exactly equal to 1 minus the cumulative function in x. Now we can generalize the expression of the normalized random variable by introducing two new parameters, a parameters named mu, a parameters named sigma, and we see that the general mathematical formulation of the normalized random variables is 1 over sigma that multiplies the square root of 2p multiplied by the exponential of x minus mu squared over 2 sigma squared. This is called also g of x minus mu over sigma. What is the property of this generalized function? It is symmetric around mu, while the standardized was symmetric around 0. And you will see better that the width of the hat is proportional to the parameter sigma. So bigger is the sigma, smaller is the maximum in mu, and larger is the function around the mean, the central value. In general, when a variable x has a normal distribution around mu with sigma, we write from a formal point of view that x is represented by n open bracket of mu sigma squared closed bracket, exactly in the symbol in the first line of this slide. The standardized normal is clearly x equal to normal of 0, 1. A specific mathematical property is that when x is normal, so the probability that x is comprised between x1 and x2, as usual, is the cumulative function in x2 minus the cumulative function in x1, and this can be written as g of x2 minus mu over sigma minus g in x1 minus mu over sigma. So now let's assume that x1 is equal to mu minus k sigma and x2 is equal to mu plus k sigma. So we are asking what is the probability that x is in an interval that is centered on mu. The probability for x to be between mu minus k sigma and mu plus k sigma can be proved. It is equal to the cumulative distribution function for the standardized random variable in k minus the cumulative distributed function for the standardized normal variable in minus k. That means, for symmetry reasons, that it is 2 that multiplies the distributed cumulative function in k for the standardized variable minus 1. This is exactly the area of the normal curve in the interval mu minus k sigma and mu plus k sigma. Specific cases are of particular interest. What is the probability that x is between mu minus sigma and mu plus sigma? It is about 68%. What is the probability that x is comprised between mu minus 2 sigma and mu plus 2 sigma? It is about 95%. And finally, the probability that x is in mu minus 3 sigma, mu plus 3 sigma is about 99.7%. So it is more or less, from a practical point of view, equal to 1. Below you see other formulations, in particular the values of k that correspond to specific values of probability. So the value of k for probability 95%, exactly 95% is 1.96, and just second example, the probability 99.9% corresponds to a k equal to 3.29. The last step of this lecture is about random variables that are computing from other random variables. So the question is how the density functions and cumulative functions of the original variables are propagated, are transferred to the function variables. Let's start by formalizing the problem. We have a function g of x defined for the real variable x, and a random variable capital X that has domain in the space omega. We can make the composite function y of omega obtained as g of x of omega. This function clearly defines a new random variable capital Y whose domain is in the set capital omega. The way is obtained through the passage through capital X. For a specific omega e, the value y of omega e is given simply by y e equal to g of xe, where xe is the random variable capital X corresponding to omega e. How is it possible to determine the density f(y) of the random variable y as a function or in terms of the density fx of the random variable x? Let's start with the equation g of x equal to y, where y is a specified number and we solve for x. Let's start with a graphical representation of the problem. You have the x-axis, you have the y-axis. Y is a function of x, so in the curved line you have an example of what we are calling g of x. There is an increasing step, then a decreasing, and then an increasing one again. Now, let's suppose you are interested in a specific value of y, for example, the one depicted in the picture. You can trace the line that is parallel to the x-axis and passes for y. Which are the values that generate y? Clearly are the intersection between g of x and this horizontal line. So they are, in the specific graphical example, x1, x2, and x3. From a mathematical point of view, it can be proved the following theorem. It is quite complicated, the proof, but the theorem by itself is not so complicated. Let's suppose that a certain value y is generated by a certain number n of points xe. I mean, y is such that y is equal to g evaluated in x1 plus g evaluated in x2, etc., etc., etc. What is the density function of y? It is given by this very simple formula. For each one x that generates y, you take the density function of x in that point, you divide by the first derivative of g with respect to x in xa, and then you make the sum of all these ratios. This is the density function of y with respect to the random variable y, exactly as it is written in the slide. This last slide closes this second step of lectures, and in order to allow you to self-evaluate, I have prepared some questions that we can read together. The first question is very simple. What is a random variable? What is the definition of a random variable? The second question is which kind of events can be specified by a random variable? Following, what is the probability density function of a continuous random variables, and what are the main properties of this function? Then, given a random variable x, how do you compute the probability in an interval a, b of the real line? I mean, what is the probability that x belongs to the interval a, b? Clearly, given the cumulative distributed function and the density distribution function. What is the cumulative distribution function? What are its properties? And what is the mathematical relation between the probability density function and the probability cumulative function? Now, if g is a real function of real number and x is a random variable, what you can say about the generic expression of y equal to g of x? What is j? What is y? How it can be defined? What happens when the function g is linear and x is uniform? For example, y equal to 3x plus 2 and x uniform on 3, 5. Are you able to make the plot of the density function of y? Consider two continuous random variables x and y, where y is again ax plus b. If the probability that x belongs to the interval x1, x2 is equal to 0, 1, what is the probability that y1 is what is the probability that y ranges in the interval y1 equal to ax1 plus b and y2 equal to ax2 plus b? Finally, we have some exercise just to practice you. Consider the experiment rolling two fair dice. Let omega equal to omega 1, omega 2 be the elementary outcome of the experiment. Build the following variables by specifying the probability distribution in terms of probability function and density function. x1 of omega equal to omega 1, x2 of omega equal to omega 2, x3 of omega, omega 1 squared, y1 equal to x1 plus x2, and y2 equal to x1 minus x2. Finally, y3 equal to x1 minus x3. What is the probability that x1 is equal to 1? What is the probability that x3 is equal to 1 and given x1 equal to 1? Last exercise, consider the random variable x, uniform over the interval 1, 2. Write the density function of x and the corresponding cumulative distribution function. Now write the density function of y1 equal to x minus 1 and of y2 equal to 3x. In particular, what is the probability that x is in the interval 1, 5 and y1 is in the interval 1, 5, and finally that y2 is in the interval 1, 5.